Now we're going to discuss the difference between bit error rate and symbol error rate. You know, in Western cultures, we raise children and we tell them that there's this entity called Santa Claus. And at a certain age, they're old enough to realize that this is actually just a story and that it's actually the parents who are giving them gifts, not this mythical creature called Santa Claus. So I think of this as when, as students in my class, you've now reached the maturity where I can quit hiding from you something I've been hiding from you from the beginning of the class, and sometimes not too effectively. I've always been talking about PE. This is done in the book too. I've always been talking about the probability of error. But the probability of a bit error or the probability of a symbol error? I've kind of tried to avoid it because I wanted to get a lot of ideas out in front of you before we had to confront what is the difference between the two and how do I relate the two. So, you know, now we understand a whole lot about probability of error. So now I can introduce to you this sort of new complication, which is the difference. So the question is it probability of bit error or is it probability of symbol error? So everything we've done so far has been one of these. Which one has it been? It's been the probability of symbol error. Of course, many, many times we're talking about the binary case. Binary case, of course, those two things mean the same thing because a symbol is a bit. So sometimes I would have said bit error, but I was careful, I think, to say bit error only when it was binary case. And every time it was an M-ary case, the probability of error we were finding was a probability of symbol error, which is good. That's how you calculate it. We were looking at the distance between nearest symbols. And so, of course, what we were calculating was symbol error rate. But now we would like to know, what is the bit error rate? Because this is going to be important when I'm comparing the performance of different modulation formats, different size of constellation. In the end, I want to compare them based on their bit error rate. So how does the bit error rate change as I change constellation size, for instance? So we're going to be looking at now how to go from symbol error rate, for which we have all the equations we need, into bit error rate. So this topic is covered in the textbook from SCLAR in section 4.9.4, and in particular it'll be focused there on gray codes, but really it's talking more generally about the difference between probability of error and probability of bit error and symbol error. So symbol error probably is what we've discussed so far. Every time you've seen a PE previously, it's always been symbol error, and often, of course, in the binary case, symbol and bit are the same. But we have to look at when a symbol error happens, what's going on with the bits behind those symbols. And so that's how we're going to be able to go from symbol error to bit error. Now there's two cases we're going to be looking at because two different kinds of modulation formats, and the equations for the conversion from symbol error to bit error are different in these two cases. We're going to take the first case, which is the easiest case, I think, which is orthogonal modulation. Orthogonal modulation is special for a couple reasons. First of all, it has equidistant symbols. All of the symbols have the same energy in the signal space. They're all at the same distance from the origin. So that makes some calculations easier. For instance, when I have to find what is the probability of symbol error for a nice orthogonal modulation, well, it's kind of straightforward because the probability that one of the bits is received in error, well, it's just the probability that that bit is received in error given that, S0 is sent. And I wanted, if it's received in error, that means I chose a different one. S0 was sent, but I didn't choose S0, which is why I have an index here of I going from 1, so it skips the right one. I'm summing over all the different ways I could make a mistake. I could have sent S0 and chosen S1. I could have sent S0 and chosen S2, all the way up to M-1. So all these are all the different kinds of errors that I could make, different types of errors. And so if I wanted to know the total symbol error, what would be the total error of making a mistake when S0 is sent? It would be the sum of all these. But the sum of all those is easy because each one is the same value, right? Because they're all equidistant. So the distance between S1 and S0 is the same as the distance between S0 and S3, is the same as the distance between S0 and Sm minus 1. So all of these, I'm adding up the same number over and over again. So there's m minus 1 terms. So it's m minus 1 times this, conditional probability. It doesn't matter which one, because they're all equidistant, so they're all giving me the same number. So I'm just going to write it as the probability that I make a mistake, which is choosing S1 when S0 is really sent. So symmetry of the orthogonal modulation makes this very straightforward. I don't have to keep track of different kinds. There's just one kind. Okay, so good. What do I do next? So I go on and I say, for any of these kinds of mistakes I can make, any of those conditional probabilities, I can really write those very simply as the symbol error probability divided by m minus 1. So this is a conditional probability. I haven't gotten to the probability of bit error yet, okay? This is an intermediate step. I can say that this conditional probability, due to this orthogonal modulation, this super symmetry, is just the symbol error divided by m minus 1. It doesn't matter which pair I'm looking at. Okay, that makes it easier. So now this is sort of my setup. Now I'm going to show you how to find the bit error. So if I want to know the bit error, what I have to do is look at the bits that are assigned to a given symbol. So if I look at an M-array system, that means that every one of the symbols will have a certain number of bits associated with it. For instance, if I have m equal to 8, then log to m is equal to 3, which means there will be 3 bits per symbol. So if I were going to look at any one symbol, I would say, well, there's bit 1, bit 2, and bit 3 assigned to that symbol. So what happens when I have a symbol error? Well, when I have a symbol error, I have to know how many of these bits are being flipped when I make a single symbol error. So one symbol error, but how many of these bits end up being affected? So let's look at this general idea of there's a whole bunch of them, up to log 2m. In this case there's 3, but m could be large. So let's just make this general. Let's look at the kth bit, some bit in the middle of this spread of bits. So I'm going to look at the kth symbol. So if I look at all the symbols, maybe I should put an example here because it gets confusing. So this could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? So there are 8 symbols. M equal 8. There are 8 symbols. Each one has a different set of bits associated with it. And one of these symbols is the right one. It's the ones I'm transmitting. So if one of these is right, all the other ones are wrong. Okay? So one of them is right, and the other ones are all wrong. But that doesn't mean all of the bits are wrong. Okay? This is the right symbol. But if I look here, this 0, well, there's a 0 here, 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 and here, depending on which one of the symbols I'm mistaken it for. Well, sometimes it's going to have one of the bits, some of the bits might be right. So that's why I say look at the kth bit. There will be m minus 1 symbols that are incorrect, and among those m minus 1 symbols, how many of them have the right one for BK? Well, the answer is that m over 2 minus 1. So you take half of them, you take out the one that's the right one that you didn't pick, and the rest of them, well, some of them, they have the right number. So if I was looking at this, 1, 2, 3, right? So m over 2 is 4, minus 1 is 3. And if I looked at this one 0, it's 1, 2, 3. And if I look at this one, the 1, it's 1, 2, 3. So if I look at any one of the kth symbols, I know that when I make a symbol error, there's m minus 2 minus 1 where there was the bit was not flipped. So how do I use that observation to go from bit error rate, symbol error rate to bit error rate? Well, the way I'm going to do that is I'm going to take the symbol error rate and I'm going to break it into 2 pieces. I know that it's m minus 1 times the conditional probability. So now I'm going to take this m minus 1 So before it was m minus 1 times this probability. And now I'm going to take that m minus 1 and I'm going to divide it into m over 2 minus 1 plus m over 2. So this m here, I divided into an m over 2 and an m over 2, right? So nothing fancy going on there. So that's what I'm looking here. I have m minus 2 over 1 times this conditional probability, and then I have m over 2 times the same probability. But now I interpret what's going on there. I interpret it and say this one is when there's no error in the kth bit. Okay, these m over 2 minus 1, that group, that had no error in the kth bit. But the other group, they did have an error in the kth bit, right? So I had, I counted before in my example, I had 3 where the bit was the same, but I had 4 where the bit was different and it made an error. So essentially, there's going to be a group of errors where there's no change in one of the bits, and another group where there is a change. And the size of these groups are, one is m over 2 and one is m over 2 minus 1. And with this observation, now I can write an equation that lets me go from one to the other, because this is the probability of a bit error. And this I can write in terms of this conditional probability. I go back to my original equation and write this part here so that I end up with an equation in the symbol error rate and the bit error rate. So I take that equation in 2 unknowns and I solve for the probability of bit error. And when I solve for that, I come up with this expression. So I say the probability of bit error is the probability of symbol error multiplied by m over 2 and divided by m minus 1. Now what I'm going to do is I'm going to take the symbol error over 2 and isolate that now. And what's left is m divided by m minus 1. And we can see that for large m over m minus 1 is going to be negligible, and it's really looks like 1/2 of the symbol error rate. So this is very intuitive. I have a whole bunch of bits in there, and about half the time I'm going to choose a symbol that had the wrong bit, and the other half of the time it's going to actually be a symbol that had the right bit. So the orthogonal modulation, with all of the symmetry associated with it, says that in this case, the probability of bit error is really just 1/2 the probability of symbol error. When I make a mistake on a symbol, 1/2 of the bits are going to be affected.